Welcome back, everyone. And now we get into the details of the fine nuances of the cache algorithm, or also of the half transform, half space properties. So one of the properties is that cache is a global correlation clustering algorithm, meaning that on the one hand, if you have two of these clusters that you see they have the same orientation or rotation and translation, they are considered as one cluster, which may be also a disadvantage because it is incapable to detect in its native form, at least, these two locally dense clusters. So it cannot distinguish and yields one cluster unifying C1 and C2 as one big one. The proof I shall yield you within the next slides why this is actually the case or why it can't overcome this. And it can also detect hierarchies of clusters of lower dimensionality that are embedded in clusters of higher dimensionality. What is meant with that? Well, we said in the beginning that cache detects d-1 dimensional clusters. So if you have a 3-dimensional data space, it detects in there a 2-dimensional subspace. This is this plane. And further, if applied and if the parameters are still met, it detects a 1-dimensional subspace, like a line, which is embedded in a 2-dimensional feature space or subspace, so to be precise. So it is capable of detect such dimensionality hierarchical subspace embeddings or clusters, to be precise. And it has a min points parameter, which mediates the support of each cluster. So if we say we want to have a cluster with at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with 10 objects, then it will consider something a cluster only if it contains at least these min points equals 10 objects. So in this case of this plane and line, it means that we have here far more than 10 objects. It will consider this as a line. And then if you reapply on this as a plane, if you reapply cache on that planar data set, it will start finding you the line on this plane. Then it has two other hyperparameters, one S and one J. Both of them mediate actually the tolerated deviation in rotation. This is the case for S and of the translation. And for this, let's look at the illustration of S. So a large S would permit like a higher deviation in rotation. So if we would choose a larger S, then this difference between lower bound and upper bound would be bigger, and we would have like more deviations here and here. While an illustration for the parameter J, the jitter parameter, it would permit a higher deviation orthogonal to that plane that we have. Or in a different illustration here, suppose if we choose here a jitter of G 0.1, then it means we tolerate also objects which are not right on this line, but which are a bit off to it. So it's like a bound around that specific line that we have detected here. So the larger the jitter, J, the more deviation is permitted, and the smaller the parameter S, the less deviation is permitted, because S is the number of bisections that we had. So just to sketch it here, if you recall, you have this half space. If you say you have one bisection, it means that you are tolerating like that much of deviation. If you have like two bisections here, then you would tolerate less deviation, something like this. So you would say I would only tolerate between this red line, what is more or less a line with a mouse, sorry. And if you go finer and finer, then you would tolerate less and less and less. So you would get finer and finer with respect to a deviation. And now let's get back to the laser pointer. What about outliers? So we know that it can, obviously, as we've seen previously in the experiments, it can recognize outliers, but how are they defined? Well, suppose here we've got 1, 2, 3, 4, 5 object functions. They have a nice intersection, An outlier is considered as one if it is outside the tolerated deviation or the scope of S and J. So since this one particular point is outside of this red box, it is considered as an outlier. Because it is far off to that object, it would be something like here or here. It is not within this scope of the jitter J or the number of bisections of this deviation that we have here. And unlike PCA-based algorithms, cache or the half transform provides a model rotation and translation. So it tells you how this plane is oriented in space, but it provides no information about the variance. So cache is not going to tell you like, look, this is the direction of the largest variance and this is the direction of the second largest variance. These informations are not provided. However, this can be achieved if you take the detected cluster and apply a PCA on it afterwards. That will tell you, okay, on that detected data, you have that amount of variance in this direction, this principal component, and that amount of variance in this direction through the eigenvalues. So this is an information which the half transform in cache does not provide. And another thing that we have here, so consider this data set. These are 3 objects here and 1, 2, 3, 4, 5 here. This center object may belong to both lines. This blue circled object here, it may belong either to the green line, which we have here, or it may belong here to the red line that we have here. So observation lesson learned from here is an object in cache can belong to multiple clusters and therefore to multiple subspaces. However, what cache is doing, it says, no, I assign a cluster to only one, I assign an object to only one cluster. It's either to the green or to the red one. Here's some discussion I wish to stimulate among you as the dear audience. In how far is it meaningful to have a unique versus multiple assignments? So what do you think about that? If you have something on discussing on this, feel free to contact me, or also to contribute in the tutorial sections about that. In how far is this meaningful? Do we wish always to have this unique assignment? Why and why not? When are cases or other cases where multiple assignments are desired? And how could cache in theory be extended in such a way that one detects or finds out that an object can be a member of multiple clusters? I mean, cache yields you in the end the clusters, but how can we go through in a post-processing step, recognizing that this belongs to one cluster or not? So this is also a challenge question for you. If you're interested, contact us. And as the last aspect here, since I promised you to answer this question with a proof, is it possible to distinguish both clusters at a specific point in half space? And now for this, let us assume that the local lines C1 and C2 are distinguishable in half space. This is the assumption that we have. Then it follows that C1 and C2, so both lines, this line green line and this yellow line, they must be 2 separate points, distinct points in half space. However, as we know, the cluster C1 and C2 can be represented by the angle alpha, so the angle that they span to that which goes orthogonal to here, and by the distance from the origin orthogonal to that line. So it would be this distance, for instance, that would go here to this line going through this small distance. However, since C1 and C2 would have the same, sorry, I have to also introduce both clusters, so C1 and C2 can be represented as objects phi1 and phi2, each of them being a tuple of an angle alpha1, delta1, and an alpha2, delta2. However, since both local clusters, C1 here and C2 here, are on the same global dashed line, it follows that phi1 and phi2, which are 2 points in half space, are not 2 separate points, but exactly the same, because they have the same angle alpha and the same distance delta. This in turn means that C1 and C2 are indistinguishable which is a contradiction to the assumption that we had here that C1 and C2 can be distinguished in half space. So it is not possible because both of them would have exactly the same alpha and exactly the same delta and therefore not be easily separable in this sense. You may, however, also argue, well, but as you mentioned before, the objects are not necessarily always located perfectly on a line. What then? Then it could be theoretically distinguishable depending how far the overlap of the two regions is, because if they are not perfectly located on a line, then you may have one rectangle or cube and you may have another rectangle, and depending on how much they overlap, you may say, yep, they belong to the same cluster, they are indistinguishable, or if they are barely overlapping, this barely overlap means one line in data spaces like this and one line may be like that, so they are barely overlapping, they do not have so much in common, then it may happen that you can somewhat distinguish. But in this extreme case, or in this idealistic case, that you have two lines, both of them have the same rotation and both of them have the same translation, it implies that you have the same point in half space, which means that you have an indistinguishable case between those two. So in half space, you cannot consider any localities in contrast in feature space, as we've seen with 4C, but you can only capture differences in the model rotation or orientation and translation. This is what you can capture. Well, this is it so far about the properties that we have here. Next week, we will also continue with half space, but not that much. So we will also go into non-linearities, since it's a bit getting boring, always dealing with linear. And we also deal with the search strategy, because you've seen this one search strategy of this bisecting of the half space. We will illustrate this a bit, hopefully better, and get more in detail into that. And then we will cover other aspects like more systemical aspects, taxonomies, differences between methods in correlation clustering, effects of outliers, the so-called term of subspace poisoning. And yes, so as mentioned, I'm a bit like a fan of this topic of half space. It even went that far that during my PhD studies in Munich, I got one colleague who said, you know what, I get you for this pre-Christmas thingy a mug. And I see how terrible it works here. So what you see here is the picture of Paul V.C. Huff. So this is the person to whom this Huff transform is called. And there's a saying on that mug, which is, when times are tough, get a Huff. And well, so this anecdote shows how much I am, I want to say was, but I still am, to be honest, into this topic of Huff transform. It may be debatable in how far this is meaningful or useful. It is at least quite interesting for me. So that you're jumping between different spaces like data space and half space, and you're exploiting different properties and limitations and what does it mean to wriggle the head around. So if you also got kind of like interested or say, there are still questions that I have to that half transform, there may be indeed questions which I cannot answer, and then you've run into the trap that I may ask you for a bachelor or master thesis topic if you don't have any. And there may be cases where I can tell you then a nice answer or a nice story around it. So this is it, folks. Thank you for attending. If you have gone even to this last 7th video, great job. And yeah, I'm looking forward to questions or to ideas. There have been seeded several ideas throughout these videos where you say, oh, but I can do it better, or can't one do it like this and that? So I strongly encourage you to do this, because as upcoming like scientists in academia or in industry, this is precisely, if that stimulates you, that's awesome. And yeah, stay healthy, take care, and see you next week then with the podcast. In this sense, bye-bye.